Hello, my name is Darren Thomas, and I am the Director of Educational Research Techniques. This is simpler, using machine learning algorithms in R. And so we are now moving into our lesson 8 here, unit 8, excuse me, and we're in lesson 3 of that particular unit or chapter, and we're going to actually develop our logistic regression model using the data that we've been setting up in the prior lesson. So why don't we go ahead and take a look at RStudio. So remember that our goal here is that we want to predict sex, the gender of somebody, based on the other variables in the model. So in line 1, we're going to go ahead and run our libraries again and set our seed for the purposes of hopefully being able to reproduce the results here in this video. Now, here's what we're going to do. To actually run the logistic regression model, you need the GLM function. So if I take a look at the GLM function, you can see right here it's part of the regular R package that you purchase. So you use that for making your actual model here. There's not a whole lot to read here. Now we're going to set our dependent variable to sex. We already explained that. The tilde sign is for setting up everything, after the dependent variable. The dot means to use all of the variables that are available. Our training set, our data set is called train. We set all this up last time. And our family is binomial. So the family is important because it kind of helps it to figure out, the proper link function to be used in the model. That's what's happening there. So binomial means that, we have two categories in our dependent variable. I believe there's something called multinomial logistic regression. Yes, there is such a thing. That's when you have more than two categories. But for our purposes, is binomial. Another commonly used family that you often see is Gaussian. That's when you have a continuous variable for the dependent variable. So having said that, we just run our model here. It's quick because the data set's not that big. And then we click on summary to get our results. And so let me make that a little bit smaller for you so you can take a look at this. Okay, so we'll just run that one more time. Okay, so there's our results. And we'll just take a quick look at that. So the deviance residuals, this is kind of a measure of the goodness of fit. It's a way of measuring error, basically. It's one way to look at it in a logistic regression model. And then down here we have our coefficients. So the thing is that with the coefficient, when there's a 1 unit increase, it increases the likelihood of something. So in our particular case, when there's a 1 unit increase, it indicates that they're more likely to be male. That's what's kind of happening there, because we're trying to predict whether someone is male or not. So if they're male, that means that they're not female. If they're not male, that means they're female. That might sound weird, but that's kind of how it works out. So when the size of the hand increases, the likelihood that someone is male goes up as well, a positive relationship. As the height increases, there's also a likelihood that they're more likely to be male. This makes sense because men tend to have larger hands and men tend to be taller. Just makes sense. Pulse is not a significant predictor, neither is age. So the rate at which someone's heart beats, if you will, does not seem to be a strong predictor whether they're male or female, and neither is their age. Again, just using common sense and intuition, that makes a whole lot of sense. And then down here we have our null deviance. That's like, no variables in the model, and our residual deviance when you have variables in the model. So notice how as you include variables in the model, the deviance goes down. The lower the deviance, generally the better. And the AIC is another measure of goodness of fit, or another metric for assessing the model. I think it's the ICINE information criterion or something along those lines. And again, you would use that to compare this model to others. The same thing with the deviance. All right. So we're not quite there yet. We need to do something else for interpreting the coefficients. Right now the coefficients are in logs, and we don't necessarily want the log ratio. We want the R ratios. Remember, R ratios when you're comparing two odds, if you will. So to deal with that, if you look closely in line 7, we're going to take the coefficients from the fit model, but we're going to exponentiate them, and that'll give us kind of like easier to interpret values, if you will. So after I run the code in line 7, you can see here down at the bottom that we have our 4 variables again. So this is what's happening when someone's hand, the non-writing hand goes at 1 unit. The odds that they are male increase by 1.87. when somebody's height goes up 1 unit, the odds that they are male again goes up 1.22. And then for the other ones, you can see that the odds don't really change that much. That's kind of how it works out. So again, what you do here is that you want to subtract 1, I believe, to make sure that this makes sense. To interpret the exponential log odds, you need to always subtract 1 and multiply by 100. So what happens here is that I would take 1.87, subtract 1, I get 0.87. 0.87 times 100, 87% there. So what's really happening is that there's an 87% increase if you want to look at it in terms of probability. Now here's the thing, with some of these it's not so strong. For example, with pulse, you can see here that it's 9.74 e to the negative 0.1. Okay, and so then minus 1, you get that number right there, negative 0.026. 0.026 times 100, you get that. So 2.6% decrease. Again, that's so small it's not very measurable. But you can see here that a powerful influence is, again, the size of the hand. When the size of the hand goes up, there's an 87% chance increase, 87% more likely that they're a male. And again, for height, you can see right there, 1.22 minus 1. Okay, so then take 0.22 times 100. If their height goes up 1 unit, the probability that they are male goes up 22%. So this is kind of how you deal with the coefficients. The coefficients tell you the odd ratio, and then you can convert the odd ratio into a probability using basic math. That's kind of what's happening here. All right. So having said that, why don't we go ahead now and assess our model. So we're going to use the same model. We're going to predict the probabilities. So here's what's happening in line 10. You have here, we're using the predict function again, and we're going to use our model, and we're going to use the type response. We want the response, whether it's male or female. And so that's what's happening. And so we're going to save this inside our actual training data set, again, by making a new column called probs. So we do that in line 10. Now in line 11, this is what we're doing. We're creating another variable inside our data set called predict. And inside that predict, we're going to repeat the phrase or the character female 123 times. The reason for 123 times is that is how many rows are in our trained data set. That's what's happening there. So this will make sense in a minute while we're doing this. Now in line 12, here's what's happening. We're going to tell R, this is what's happening. Right now, every row in the predict column is female, but we want to change it. If the probability is greater than 0.5, we want to change it to male, because 0.5 or higher means that the model is more confident that the person in that row is a male rather than being female. And so this is how we'll have our collection of males and females. But before I do that, I just want to kind of show you what's happening here because it's getting kind of abstract. So we do view, and then let me zoom in for you. Here is what's happening. So you can see right here, these are the variables I started with. Sex is my dependent variable, the size of their hand, their pulse, their height, their age. This is all stuff we started with. The probabilities, we just put those in there when we used the predict function. All right, and then we created this column called predict. But notice how everything in predict is female, because remember, we told it that to begin with. Our primary goal here was just to create the column, to create the variable first. It wasn't to set it up just yet. So having said that, if we go back here to our data, our code, what we're going to do now in line 12 is that if the probability is greater than 0.5, we want to change it from being female to male. That's what we're going to do right here. So if we go back and take a look at the train, you can see now that it's been updated. So right here, one person's been changed to male. Why? Because the probability is 0.69, which is above 0.5. That's why we did that. Now going back here, we're almost done. Let me zoom out because I'm pretty much done with that table. Okay, so now what we're going to do now is we're going to look at our confusion matrix. We haven't talked a lot about that, but we want to see how many men were correctly classified as men, how many women were correctly classified as women, etc. And so you can see here, this looks pretty good. 61 females were classified correctly, 46 males were classified correctly. There was only 16 misclassifications, And so if we want to figure out what our actual accuracy is, we just use the code right here in line 14. What is basically happening is that we're going to take the mean of train in the predict column with sex. That's what we're going to do here. And you can see the accuracy is about 87%. Again, that should not be surprising given the variables that we are using. Men almost always have larger hands. Men are almost always taller. This was a pretty easy model to generate. And so that's kind of what happens in this particular video. So let me go back and make sure things are clear. So in this video, we made our logistic regression model. We were trying to predict sex based on, the size of the hand, how tall they are, their height, their pulse rate, etc. We used the summary function to get a look at the different coefficients, and then you have to, of course, convert or transform the coefficients from log ratios to normalized regular exponentiated logs where you get rid of the log function. Now, when this happens, it gets very confusing. What you have to do is that first you get the R ratios, which is like, okay, if this goes up 1 unit, this person is 1.23 times more likely to be male, whatever. But if you want to get the probabilities, you have to subtract 1 from the exponentiated coefficients and multiply by 100. And so what we learned, again, because this is kind of confusing, is that right here, if you subtract, you get 0.87, which means this, that if someone's hand goes up 1 unit, they're 87%, the probability, they're 87% more likely to be male versus being female. And that's kind of how that works out. And this is how you interpret logistic regression. Now, after we did that, we calculate our probabilities using the predict function. That was very, very important because it was telling us who they think is male or female. We then put that inside a column that we created called probs. We then created a column called predict, and we made it 123 units long for the purposes of being able to use it in the future. And then we wrote over it. So we didn't make it a third column. What we did was we took the existing predict function, or the predict, column, and we overwrote it. So if the probability of that particular person was greater than 0.5, we made it male. And then lastly, in lines 13 and 14, we made our table and we calculated the accuracy of our model, which is actually very good. So that concludes this video. In the next video, we will actually test our model to see how well it does with the test data. So I hope this video was useful for you and that you were able to understand what we were talking about. Some of the things about logistic regression can be a little confusing, but I'm hoping that you were able to interpret this and understand. So my name is Darren Thomas. I am the Director of Educational Research Techniques. This is simpler using machine learning algorithms in R. Thank you.